Hi guys, this video is about Schrodinger's wave function and the infamous Schrodinger's equation. So we are going to have an insight at a very interesting phase of physics when the quantum mechanics, what we say is the truth, the reality, the how particles behave, that quantum mechanics was being developed, and the equation stands like a pillar. It's same as your F is equal to ma in your classical mechanics. So understanding the equation is going to tell us what this quantum world is about and how quantum particles behave, and it is very much required for studying your atomic structure, because when you go to that minute level, we have already discussed that our classical mechanics is not going to hold right. The classical physics is not going to hold right over there, and since it was not holding right, we had to develop something. So Bohr started work on it. Before that, Planck found out something. So we have a history of that. We have already discussed that. Just to have a quick recap, you had Planck and Einstein figuring out that energy itself is coming in packets. The light itself is coming in packets called photons. Then electrons, which can absorb energy or release energy in those packets, would have some definite energy levels, and it can't exist in between. And that was the thought process of Bohr, and he gave the Bohr atomic model, where electrons are in the first orbit or the second orbit or the third orbit and nowhere in between. So they can exist only in those, and when they jump from one orbit to the other, they are going to give out a packet of light, or they are going to take in a packet of light, depending on whether they are jumping to a lower shell or they are jumping to a higher orbit, in fact not a shell. So that was what was given by Bohr. So it all collaborated with the finding of those times with the spectral line first of all. Because of the observation of those spectral lines, these deductions were made. But then in those very spectral lines, there were fine structures. There were structures which could not be explained by Bohr's model, and the energy was not that discrete that it is jumping from one orbit to the other and there is nothing in between. There were stuff in between. So there were spectral lines around the lines what was found out by Balmer, Paschen, so the Lyman. So these fine lines were not explained by Bohr's model. So eventually he was doing a lot of work and he was explaining all the things, but his model, he himself knew that his model is not explaining everything. So his model was proposed in 1915, and we are now talking about around 1925, and de Broglie has come up with the equation that every matter, he has come up with a theory that every matter is a wave also. So we have dual nature of everything. Anything is a matter, is a particle as well as a wave. So that theory has come up, and it has been able to explain the radius of electron in hydrogen atom also. So, and it tallies with the Bohr's postulate. So the Bohr's postulate was not totally wrong. Where Bohr said the electron will be is there, and there are other places. So we have to do further work. So this theory that matter is a wave has got established by various experiments also. Particularly the double slit experiment, where the pattern which is given by a wave, the same kind of pattern which would have been given by a light, a wave, the same pattern is observed to be given by electrons. So electron beam is giving the same pattern. By the way, when you observe it, it is not giving. So I should not use the word observed. When you're not observing and the pattern is getting formed on the screen, and then you study the screen later, you are seeing that it had behaved like a wave. But if you want to see it behaving like a wave, if you want to see what it was doing to give that pattern, then the electrons are not behaving like a wave, they are behaving like particles. So again, I can put a link of a video where you can see the double slit experiment, but I don't want to go into that. I don't want to start drawing the interference pattern and all. So because I don't want to shift my focus from what I want to do, that is wanting to understand what is the meaning of this. Because when I read this first, I had various things in my mind, that what would a wave function mean. It's a funny name. So function itself is a funny name. When I heard of function first, that this thing is called function, it did not, I mean, what it did and the name, this somehow did not match in my mind. So anyways, so what is wave function is what we'll try to understand, that what do you mean by the word wave function, by the terms wave function. And then I'll write down the Schrodinger's equation, that big fat equation, and take out your fear of that equation by understanding some of the terms, what we can with the math, what we have learned till now. We'll try to figure out, I'll try to show you what that equation means, so that when they say it's a time dependent equation, it's a time independent equation, this is that, and you have this operator, that operator, you're not having a big fear of it, and you're understanding what is meant over there. Because even though it is not required to solve the equations ourselves, or it is not required to know the parts of the equation, without mentioning the equation, we can't go on to the conclusions. The conclusions is the part which is required, and the conclusions are quite simple, and the model which is made based on the equation is what is required. But then we can't jump on the model that there is some equation and hence the model is there. So we have to name, we have to write that equation. So that understanding of that equation, what it is good for your self knowledge. Don't worry, it will not get tested, it will not get tested at all. So, and what comes for some of the tests, some higher level test, is a small part which I'm going to show. So when you know the Schrodinger's equation and you know what the solution will mean, you'll understand a lot about the subsequent theories. So we are going to dissect and get as much as knowledge what we can get with our present knowledge on this Schrodinger equation, and then based on the solution of the equation, we'll get the wave function is there in the equation. In the Schrodinger's equation we have wave function. So when we solve the equation, we'll get some solutions of wave functions. So that wave function is going to represent probability of electrons in certain space. So that spatial diagram we are going to draw for various wave functions what we can get out of the equation. So we'll have various wave functions, and all those wave functions will give you various solutions, but those solutions are discrete. It is not like all over the space. So you have, I mean, literally it is all over the space, by the way, because there is probability of the electron being anywhere and everywhere. But then there are higher likely places where it can be and lower likely places. So it is the solution of these equations is going to give us the wave function, which is going to tell us where the electrons can be found, and those houses of electrons are called your orbitals. So we'll draw some orbitals of the s, p, d and f kind, and then where it can't be found, where it can be found are the orbitals, and then where there are some locations where it is mathematically having zero probability of being there. So those points will be called nodes, and then we'll be studying how when we go radially outside, where all are the radially outside from the nucleus in an atom, where all are the probabilities of not finding an electron, so not finding an electron. And then when we change the angle, when we go angularly, then here you have a probability, then there you don't have, then here you have, you're not going radially. So all those places will be your angular nodes. So we'll discuss the radial nodes and angular nodes, and then we are going to write some wave functions, and then we are going to solve those wave functions. So it will be a big fat function, and we'll try to solve that where does the wave function or the square of the wave function become 0, so that we can get a node, 0 probability, and where does it become highest, so that we can say that Bohr meant this radius, at this radius it would be that kind of thing, where is the probability highest. Okay, by the way, Bohr got all the radius which you can say is equivalent to the shells, and he did not get all the various shapes it is possible. So he was more in a 2D kind of thing. So those orbits were in 2D in a plane where the electrons can go round and round. But this probability, these orbitals and the spatial diagram with the probability of where you can find is a 3D structure. So so yes guys, that's it. That is our aim for the class, and so we shall start with wave functions now. Yeah, so as promised, let's understand this wave function. So wave function, so let's break it up in both the words and go word by word. So which one would you like to do first? I guess this is easier to understand. So what do you mean by a function? What do you mean by a function? As we have done earlier, fx is equal to say x square plus 2. What is that? That's the function. You put some value of x, say 1, f1, it is going to give you an answer of 1 square plus 2, which is equal to 3. So function, we all know what's a function, so not a big deal over here. Okay, now what is wave? Now, when we think of wave, generally what comes to our mind is a mechanical wave, say a wave on a string, or the waves which is on the water surface, which is coming on the seashore. You would have seen on the televisions at least, if not for real. So those waves which are coming is what comes to our mind. So wave function, whether it means those kind of wave or not, we'll come to that later, but at least we'll try to understand what is a wave, the meaning of the wave in the normal sense. So we'll go to what it means in the quantum sense a bit later, and we'll come to that. But wave in a normal sense, let me just describe with a wave which is going on a string. So if I have a string and I give a jerk on this end, so there's a long string without, I don't want to make an end over here and get the wave reflected. So it's a long string and I'm giving a jerk over here. What happens? A pulse is created. That pulse is going to go forward. If I keep on jerking the string, if I keep on moving the string up and down, so what is going to happen is continuous pulses will be created, and I'll move it up and down also. Like here, the whole motion. So what will happen is, after a while we can see continuous waves created. This you can do at home, and what you will see that this seems to be going forward, but we know that it is not going forward. It is not going forward. It is a traveling wave is what we are seeing. We know that the particles, any one particle is just going up and down. So say this was a string, the particles are just going up and down. The particle is having this kind of motion. It is going up and down. So if I want to study a particle which is say x distance away from a certain starting point, if I want to study this particle and I want to describe the motion of that particle, now mind you, will this particle come to the highest level? It is going to come to the highest level once the wave, say this wave is traveling and the wave has come forward, and this wave, this peak will ultimately reach over there. So this particle is going to go up and down the whole amplitude. So this much is your amplitude. So it is going to go up and down fully, and the location, the y location, if I call the height of the particle as y, or I'll rather call it as fx, so that we can have that function thing going on over here. It's a function of x. So if I call the location as a function of x, it may be something like a sine kx, where x is the location and then the sine thing is varying. This sine value can vary from -1 to +1. So this location, the y location, the height where the particle can go from a -a to +a. So that's your -a height and that's your +a height. But we also know that the location will depend on a certain time. At what time? We are asking about the location at what time. So it is not only that height is not only going to depend, say the height is y. So the height is not only going to depend on which location we are talking about, what is the x, but also what is the t, what is the time, at what time we are talking about. So when we write a equation a sine omega t minus kx, this equation you will be writing yourself after you have done a chapter called SHM, simple harmonic motion. Once you have done that, where you study a particle going up and down, up and down, up and down, and you describe the motion. There is no traveling over here, it's just standing over here. The particle is going up and down, so each particle over here is actually going up and down. So once you know how to describe that up and down motion of a particle, that's your SHM chapter, it's a full chapter for you. You would be able to write that SHM for various particles. When you write the SHM for various particles all over, SHM for various x's, x here, x there, x there, x there, you are writing the equation of a wave. Now what do you mean by equation of a wave? Equation of a wave is giving you some description about the thing. With the input of the location and the time, with the input of what location and what time you are talking about, you can get where the particle is. You can do something to the where the particle is information and get the velocity of the particle, perhaps like it is going up and down. You differentiate this up and down motion with t and you'll say that the velocity of the particle going up and down is so much. Once you get the velocity, you may be able to find out the energy. So with the equation, with the wave equation, you'll be able to find various things once you know the description of the wave. So this wave equation, that gives you a certain description of the wave, and you can get out various informations, whatever information you want. Like this is not an equation of a power, but I can get the power transmitted by the string if I want to, by using the equation once I have known the equation. So similarly, this wave function, so I can call it as a wave function, I can call it as a function. It's a function of x and t. It is describing a certain wave. Get the point? So the wave function term means same thing in quantum physics. But in quantum physics, you might ask that what is the thing which is waving, what is the thing which it is describing. Like over here, it was the motion of a particle located at a certain x. That particle is going up and down. So you may ask what it is describing. So we'll come to that. So I hope you have understood that how a wave function looks like. This is one format of a wave function. By the way, this is in course, and what else also is in course is if you have any term, any function which has this kind of component in it, any function of x and t which is having a omega t minus kx, which is having whatever omega t minus kx in it, it is the equation of a wave. It's the equation of a wave. So I can just write down a sample equation of a wave. A sample equation of a wave may look like, say, f xt is equal to a e power omega t minus kx. That is the equation of a wave, because we have this term. Why this term tells you it's the equation of a wave, will do. I'll be telling you that when we do this chapter. So it's not a big deal. It is something like, if I have written the equation, time dependent equation, of a particle which is going up and down, another particle has to behave the same way after some time. If it has to behave the same way after some time, we call it a wave, and will generate such a equation. So now we have known a lot of things over here. So in fact, in the same breath, I can just write down the equation, or let me just wait. I was just planning to write down the equation of the kind of wave what has been considered in the wave function, the kind of equation which is there. Is it like this, is it like that, or something else? But then we'll just wait and come to that in a while. So I hope you have understood the literal meaning of wave function. What's a function, what's a wave? So that's the literal meaning. What does wave function mean in the Schrodinger's equation is what we are going to come to. But mind you, Schrodinger himself did not know what the equation meant. I mean, what it can represent. He thought it is something kind of a charge which has been dissolved or smudged in the space. I'll come to that. So what is the meaning of wave function is a bit later. Why he was finding and how, what he was finding, what was he finding when he was writing the equation is what I'll try to tell you. And the history goes something like this, that he was giving a lecture on the de Broglie's wavelength. So we have all done it earlier. So de Broglie. So it had been well argued and proved by some experiments that electrons are behaving like waves, and so all particles are in fact behaving like waves, and those particles have an associated wavelength, and that wavelength is given by that equation of de Broglie. So the wavelength is given by this. So Schrodinger is being asked that if it is a wave, then how do you describe the wave? What is the equation of the wave? So he goes in a quest of finding what is the equation of the wave is what he gets. That's your Schrodinger's equation, which describes the wave, what de Broglie said. So just understand the sequence. De Broglie said, de Broglie with the de Broglie's wavelength, it was proved that standing waves would be formed. Standing waves, I'll describe that also. Standing waves would be formed when your circumference in which the electron is taking around 2 pi r is integral multiple of de Broglie's wavelength. Right, the circumference is the integral multiple of de Broglie's wavelength. Then only you'll get a standing wave, and standing wave is a situation which is a possibility that yes, electron is existing if it is a wave. I'll describe that what I said. So now get this very clearly. Waves interfere with themselves. Waves interfere with themselves and they can cancel each other out. Meaning to say, if you have, say, a blue light coming like this from a certain source, somehow you got a single ray, what you can call as a ray or a wave, and another blue light coming from this source, and they meet at some point. Surprisingly, had it been only one source, you would have seen a blue spot. Had it been the other source, you would have seen a blue spot. If both are coming together, you'll see nothing. You'll see nothing. You'll have a dark spot or nothing. You'll see nothing. That means this wave has cancelled that wave. This shows that light is having a wave nature. So there are a lot of things which shows that light is having a wave nature, because waves can cancel out each other. If you do a normal arithmetic addition of that wave and that wave, the wave I showed, the wave equation I wrote, you will be adding and subtracting those kind of waves when it is superposed with other waves. So it can cancel out. Now electrons, if they are waves and they cancel each other out, then there will be no electron. The charge is gone, there is nothing, which is not happening. We know if a certain charge is there, a certain charge is there. It is not like it is gone. For them not to cancel each other out and to be confined in a certain region, we'll call it as a quantum space. So your atom itself is like a quantum space. For the electrons not to cancel each other out and them to behave like wave, they should form standing waves. Now what are standing waves? I'll try to put an animation of standing wave over here, and in the meanwhile I'll try to give you a link to one of the free YouTube videos. I'll try to find one where a standing wave is well it has been shown well, where you can understand it has been depicted well. It's not a very difficult thing, and standing waves are what you are going to solve in the chapter of waves. What I said will come after SHM. You are going to solve standing waves, so it is there very well in the course, and with a bit of math, what you will be learning all along in these 2-3 months, you would be well equipped to solve those kind of things. So I guess a little more math which is going to happen in your college, you can solve this. So a lot of solution of Schrodinger equation, one full semester will be, you'll be solving it. So but what are you solving? What does it mean? Has got a greater depth than the solution itself. You can see a 5-minute video on the derivation of that equation. So was that equation derived in 5 minutes? Obviously not. Okay, so what was I saying? A standing wave. Yeah, so again I've taken a string. Now I've put a wall over here and I'm sending some waves on this. When I send a single pulse, mind you that pulse travels over here, hits the wall, and since it cannot jerk the wall up, it gets jerked down. Same as your laws of reflection, you'll have an equal and opposite reaction. It will try to jerk the wall up. It is putting all the particles up. Want to put the wall particle up, but the wall particle up is not going to go up. Gives an equal and opposite reaction and jerks this thing down, and the pulse reflects. It goes down and comes back. So this pulse which was going forward, it comes back. Now when it comes back, it is going to interfere with more pulses which is going to go forward. So you have not sent only one, you are sending a continuous wave, as I was showing. So if you are sending a continuous wave, you have continuous reflections from the other side, and what you'll see is, depending on how fast you are jerking and all, how fast you are moving this string up and down, what you can see is, you'll see a very beautiful pattern formed, and you will no longer see that the wave is traveling forward. You'll no longer see that this pulse is going forward like that. It is going forward on the string like that, but you will see, what you'll see is a wave kind of shape. This is the wavy shape which is just going up and down and not going forward. So you'd rather see the video. So here the particle is going up and down. Here also the particle was going up and down. But what is the difference in this particle going up and down and this particle going up and down? This particle will always have a max amplitude of so much. This particle will have a max amplitude of so much. So that's a standing wave. And what is a traveling wave? Any particle will have a max amplitude of this A. This point was A up. After a while that point will be A up. After a while that point will be A up. Now when it reflects and when they interfere, which you'll be solving, what you'll see is things which will be going up and down, and any one given point will have that much of an amplitude. At a certain instant you may see the string all flat. If you can observe the guitar string very closely, you will see the same thing. It vibrates, and you can see a blurry shape like that, and then coming back and going up. You can see that. That's so this, at a certain snapshot it may be like this. So particle in this red one, this particle has gone so much up and it is going to go down, but the maximum up it will go is there, maximum down it is going to go there, and it no longer looks like a wave which is going forward. Like on the surface of the sea, you see a wave which is traveling forward. This is no longer a traveling wave, and it is just SHM of all particles just going up and down. So if the particles are going up and down and due to a wave superimposing, it is called a standing wave. So this is what is a standing wave. I'll give you a video so that you understand. I'll try to give you a video where practically somebody is forming that standing wave, because it's not a big deal to form. Why I'm emphasizing it's not a big deal to form. The particles themselves want to arrange in a certain pattern such that the energy is suitable. That is, it is in the what you can say is the least energetic state and not in a random state. It has organized itself, I would say. It has organized itself. So here again, when de Broglie's equation was verifying your Bohr's orbit, standing wave was being formed. Standing wave. So it is kind of electron here, electron there, electron not in between. So I'll come to that, what it can mean. So standing wave was being formed. So it was clear to Schrodinger that if the electrons, if the wave which is going forward and coming back, mind you, let me just tell you another thing also, that if this wave was here and this wave had come over here, at that time you will see the string absolutely flat. You won't see the string up and down. The string is not going to split for you, half up and half down. If it doesn't split, by the way, then it will be absolutely flat. So it has vanished over there. Now electrons being wave cannot vanish. So some charge has to be there, because we know that that region is having a certain charge. At a certain instant of time, there is no charge. We can't say that. So that's the key. It's key, and it has not been written in many places. So I'm saying again, at a certain instant of time, there is no charge. You cannot say that. There is, the total charge is that distributed here and there is what you can at the max guess. What was the guess of Schrodinger at that time? So basically he wanted in a 3D space to solve the equation, to get the equation from the fact that these are standing waves. So he took help of a solution which had been there earlier by this guy Adrien Legendre, a French guy, lifespan from 1750 to 1833. I just looked it up in the Wikipedia. So this guy had given an equation of 2D waves. Just now I showed you, like on a string, on a one dimension, how would a standing wave look like, and then you will be writing an equation of the standing wave yourself, and that equation will somewhat look like this, that y location of a particle is a, somewhat like this. That means at a certain location x, it will have a part of a cos kx, sorry I missed a s over here, cos kx is less than 1, we know that. So at a certain location x, your amplitude, this part will depict your amplitude, will only be a part of a, and when that will be the amplitude of a SHM. This depicts an SHM of the particle happening over there. So this is the solution of a standing wave which you will be doing yourself. So all this is going to make more sense after a year when you have done all this stuff. But then unfortunately this lesson is right in the start, and it refers to so many things which in math and physics you are going to learn later. But anyways, when you watch back this, you'll understand more, and don't worry if you don't understand this at all. Don't worry at all. So the point is, we can solve the equation of this kind of diagram. We can solve that equation of that kind of diagram. And this is on a string. This guy gave a much more complex solution for an actual space, for tidal waves he gave. So you are not only on a one dimension, you have gone to 2 dimension and 3 dimension. So he has given a solution for an actual space for standing waves. So so Schrodinger borrowed possibly this equation, and he borrowed the Hamiltonian mechanics, which was also developed much earlier. So that was again 1800 something. So I don't know the exact year. So this Hamiltonian mechanics is like a parallel to the classical mechanics of Newton, and it describes if you have the Hamiltonian, if you put the Hamiltonian operator, there's something called Hamiltonian operator which will come to when we are writing the equation. This will describe the total energy of a system of particles. So there are a lot of particles, and all those particles total energy has to be described with kinetic and potential energy. We can do it by Hamiltonian mechanics, and the way it is done, the operations which has been done can be listed as a single operator which is called Hamiltonian operator. So your Schrodinger equation is having all these influence, and he comes up with the equation where the wave nature of the particle is described. Now that equation is fully fitting in whatever is being observed by experiments. You had those extra spectral lines which were coming, those fine structures which was coming. In fact, the fine structure of the doublets will come later, so ignore this doublet part. So apart from, okay, so I can say that all the failures of Bohr model was taken care by this, and this Schrodinger equation took over the Bohr's model, and it also described the quantum nature, because when you solve the equation, the equation is getting solved in quantums. It is getting solved in integral differences. There are some variables which can be either 1 or 2 or 3 or 4, and then there are other variables which can be either 0 or 1 or 2 or 3. So it is being solved in those integral. What I can say over here is, if you can see that for a certain frequency you'll have 3 balloons like that, right? You'll have 3 points where there is 2 points where there is no amplitude. If you can count this also, that also, then 4. Otherwise these 2. Get the point? These 2, by the way, in the string also they are called nodes. In a wave function also, where you will not find, where the probability of not finding the electron is there, is also called nodes. So now I'll not talk much in terms of probability, because I have yet not told you that what this wave function, by God, I missed one thing, that is the symbol. Wave function is written by this symbol, the letter psi. So that's the letter which describes wave function, and there are various formats of the wave function. So I'll come to the format. Let me just finish off with this thing. So the thing is, when you solve for the wave function, the solution automatically is coming. It is, as they say, the natural solution itself is quantized. You have this solution. It is coming in numbers, as when you solve a quadratic equation. What will happen when you solve a quadratic equation? X minus 1 into x minus 2. What are the solutions? X is equal to 1, x is equal to 2. So similarly, you have solutions of this equation, and those solutions are discrete solutions. It's not like a continuous thing. It's a discrete solution, and hence the numbers which pop out of the solution are called quantum numbers, like n, l, m. These are the numbers which are popping out of the solution of the wave function. So again, when I'm describing the wave function, I've almost gone into describing your Schrodinger's equation a bit. I have not written, so I have not as I promised earlier, we'll be dissecting, we'll writing, and we'll take out the fear of that equation. So we are just having a general discussion on that. So when you solve the Schrodinger's equation, you're going to get various solutions of that wave function, and those wave function solutions will have dependency on integral numbers like n, l, and m. Get the point? There's no s right now. S comes later on. You have these three things, l, n, and m. You can say that it is depending on n. I'll write the equation and I'll describe this better. And then l is also described in terms of n, like it is depending on a variable n. So when those variables are coming out of the solution, and when you see that, say for a given n and l, for n is equal to say 2, l is equal to say 1, when you are putting various m's, when you are putting a m equal to 0, these are just integral solutions of the equation. We don't yet know what is the meaning of it. When you are putting m is equal to 0, m is equal to say 1, m is equal to minus 1. When we solve for the energy, it is not showing any change in energy. It shows the same energy when we are solving for the energy. But when we are solving for say the function itself, when we are solving for the function itself, it is giving various answers because the function is depending on your n, l, m. When I change anything, it is giving a different answer, but it is not giving a different energy. So we are trying to plot the spatial diagram by doing a 4 pi r square and psi square, and then we can see that various m's is going to give you various different locations, different orbitals. So this can tell you the orientation of the orbital. This can tell you that the angular momentum in such orbital can be of this kind of angular momentum, whether you are in this shaped orbital, which is a p, say a p shaped orbital, whether you are like this or like that, your angular momentum is same. The m's are different for this and this. Get the point? So your n and l is same and m is different. So in fact, forget about the last 1 or 2 minutes, forget about this and this and this, because anyhow I'm going to come to that and I'm going to describe it well to you. So let me just round up our discussion of the meaning of wave function. Now yet have we understood what is the meaning of wave function? Now what we have understood is Schrodinger found out an equation such that electrons, which is around, he went for the hydrogen atom model, okay, the quantum space in which he is wanting to describe the behavior of the electron is the hydrogen atom. So what we have understood is he has agreed with de Broglie that it's a wave, and then with the concept that it has to be a standing wave. So for it, in that space, to be a standing wave, he writes a certain equation which should have so much of an energy. So that energy of a distributed system is given by this Hamiltonian mechanics. He uses that. He uses equations which can lead him to write the equation of standing wave in 3D, and he gets a equation. Now he has got the equation which is describing everything all right, which is describing, if you want to figure out how much is the energy, it is giving you the energy. If you want to extract some information out of that equation, it is giving you that information. So this equation is a hit. It's a hit. It is able to take care of the things which Bohr could not. But then what does this wave function actually physically signify? It is clearly not that the electron is going in a wave. It is not that. The electron is going like this. No, it is not like that. Okay, Bohr said electron is going round. Okay, it's going round. So what is it? What is it which is actually waving over here. So what he thought, mind you, he gave an interpretation of his own equation which was not right, and very soon he understood that it is not right, and somebody else, Max Born, gave us what it can mean. So what Schrodinger thought, we'll go in the chronological order. So what Schrodinger thought is, it is the distribution of charge density. Electron is a charge, and then electron is waving. It's not actually waving, so it is supposed to be a wave. So what can that wave mean? So where the high amplitudes, a wave will have amplitudes high and low. So you have this big amplitude over here. What does that high amplitude means? He said that the high amplitude means where the charge density is more. So it was in the space around, you have charge densities, more charge density, less charge density, more charge density, because electron after all is a charge. So that's a good explanation what he is thinking. So the kind of thing what is coming in his mind is one electron, which we thought is 1.6 into 10 power minus 19 coulomb charge. It is that much, it is one electron is that much charge, is actually smudged, it is dissolved. I think in some text it is said that he used the word dissolved, and some part of it is here, very less part is here, some part is here, very less part is there, some part is there. So the charge, that one E charge, which is the fundamental of a charge, which is called an elementary charge, that itself is smudged, which was not a possibility, which he agreed very soon that it is not a possibility. Because when you start locating it, one of the reason, when you start locating the electron, when you want to see where the electron is, it comes at a certain spot. When you want to see where the electron is, the Schrodinger equation collapses and you get the electron at a certain spot. It is no longer a wave and you get the electron at a certain spot. So if it was a smudged charge actually and assembles together and becomes one, it will give you massive magnetic field. It will give a total collapse of your electromagnetism, what we have understood till date. That cannot happen. That means the time interval in which you can observe, that time interval will dictate that how fast the electrons which is smudged around can become together into one. So that will give you a kind of current. So that current is going to create magnetic field, which can create like immense magnetic field, which will defy conservation of energy also. So the thing is, that was not happening. That was not happening. So it was not the electron which has been smudged here and there. The thing was, electron is somewhere at one place. It is at one place. So this was the big controversy, okay, afterwards with Einstein. Max Born, very soon after the equation came, he came with the interpretation what this wave function can mean. So he said that it is depicting the probability density of where the electron can be. The electron is at one spot only, but we don't know where it is, and it is not because of the lack of information that we don't know. It's not like Einstein said it is because of lack of information, by the way. He said that it cannot be fundamentally that we can't know. So that was his theory, and he died thinking in those lines, even though he was the father of quantum mechanics in a way, you can say. So he initiated everything. He had all the thoughts going on, but he hated to believe this, that you actually don't know where the electron is. It is not like you don't have a device to find out. So this uncertainty principle is a fact for sure, and it is not a limitation because of human means. So as a fact in quantum world, you can't say where a thing is. What you can only say is what is the probability of being there. What is the probability of being there? And when you do the search and when you try to find, you'll find it somewhere at one spot. You'll find it somewhere at one spot. If you do a statistical analysis and you do hundreds of times, then the most probable spot, you'll find it more often than in the less probable spot. So which was coming right? Which was coming right from the equation, and hence it has been agreed that yes, this is depicting the probability. Now this equation has got a negative in it. It can go to negative also, positive also. The square of the equation is always positive, so the square of the equation is depicting the probability. So that is one thing. Plus, if you see the probability distribution all over of anything, the total probability can only be 100%, which means 1. A total probability can only be 100%. If I say I'm 100% sure you're there, that's it. I can't say I'm 200% sure. That is not mathematical. I'm 80% sure, 80% is the probability of you being there, then there is 20% of probability of you being somewhere else. 80% there, a 15% somewhere else, and a 5% somewhere else. If you add that 5 and 15 and 80, you'll get 100. So this gives you a probability distribution, which if you add up all the probability distributions, okay, you will get a 1. So that is coming with the square of it. So two things, it is giving a total probability of 1 when you add up the probability distribution, and the probability has to be positive, so it is a square. You can say in those terms also. Yeah, so what is the meaning of that term wave function? The wave function is giving you the probability density. Square of the wave function, in fact, is giving you the probability density, where you can find an electron. What is the probability density? So in fact, to get the probability, you'll have to multiply with the volume of the area what you are talking about, of the region what you are talking about. If you get the volume of the region what you are talking about and multiply with the probability density, then you are going to get the probability. So we'll do that in a while. So right now what I want you to understand is, after getting the equation, they figured out that this function can mean this. Whether they would have figured out that the meaning of the function is where the electron probably can be or not, does not change the fact that Schrodinger equation was the key in finding out all the aspects of the electron in the atom. So you can find out all the aspects of any quantum particle, if we can say it as a particle, any quantum object. You can find out all the aspects of it, like energy, say momentum, location, all those things you can find out using, location is like in a probability thing, so you can find out those things using the Schrodinger's equation. So that is what the Schrodinger equation is, and the Schrodinger equation has got a wave function in it, which is now clear that it means the probability. It means it depicts, in fact, it depicts the probability density of finding a quantum object at that place. Okay, now let us go on to the big fat Schrodinger's equation.